What is ICDF? Well, ICDF, it's inverse function to CDF. Before we start discussing this function, let me remind you what inverse function is, okay? So we can define a function that gives a value y for any value x. For example, if you have a function y equal to x squared, and then if x equal to 2, y will be equal to 4. If x equal to 3, y will be equal to 9, and so on. So that's the function. So we can say that f of x is x squared, okay? What is an inverse function? Inverse function does the opposite. So inverse function, usually it's denoted by f minus 1 y. It's a function that for any value y gives you the value x. What will be the inverse function for y equal to x squared? Of course, it will be x equal to square root of y, okay? Let's check. If y equal to 4, the square root of 4 is 2, so x will be equal to 2. When y equal to 9, square root of 9 is 3, so x will be 3, okay? So the normal function gives you value of y if you know x. Inverse function gives you value x if you know y, okay? Now, what do we know about CDF? We know that CDF gives us a p-value. So, for example, p equal to fx, okay? What is this? P, it's a probability, right? What the probability is? It's a probability. So p, it's a probability. Let me call it x0 again. It's a probability to find a value which is equal or below the given, okay? So it's an area on the left in the density distribution curve, okay? So it means that the inverse ICDF, so this is CDF, so the ICDF should does the opposite, okay? So it means that it should gives you a value x0 for a given probability. So the probability is still the same. It's a probability to find a value equal or below given, okay? For example, you have some theoretical distribution that describes your data well. And if you want to find out, let's talk about height of people. You want to find out how many people have height below and equal to 165 centimeters, okay? So that's exactly what the CDF does. So you can just take the f of 165 and get the answer, okay? Imagine that now you want to do the opposite. You want to find the value. So now your value is not known. That gives you, for example, the first quartile, so 0, 25. So you need a value for the first 25 smallest values, so 25% of the smallest values. In this case, you know p, this is known, but you don't know the x0. And in this case, you need to use the ICDF, f minus 1 of 0.25, which will give you this value, okay? So that's the idea of ICDF. If you know the probability and you want to find the value that corresponds to this probability, you use ICDF. But if you know the value and you want to find a probability that corresponds to this value, you use CDF. We will talk about some examples later. Now I'll just show you a couple of ICDF functions. For example, in this case, you can see this is the probability. It's p, actually it should be p here. And this is some value. So let's take the second one. Let's say you want to find the percentile, the 20th percentile. So for the 20th percentile, the probability is 0.2. So this is 0.2, and this is the value. Okay, so let's say it's 54, sorry. So it means that 20% of the values are equal or below 54. So that's how we use ICDF. You can think about ICDF as a quartile function. The same function that you remember we used some linear approximation to estimate quartiles. If you know the theoretical distribution, you don't need to do any linear approximation, because in this case, ICDF is a function that gives you quantiles. For example, if you want to find the first quartile, you just need to call this function for the 0.25, because you have 25%. Or if you want to find the 90th percentile, you just call this function for the 0.9, which is the 90th percentile, and so on. So we use ICDF to find the values for different quantiles. To summarize this lecture, I would like just to repeat a couple of most important things. First of all, it's a parametric approach, how we use parametric approach in statistics. The idea is following. First, we find a theoretical distribution that fits our values well. So it fits our empirical real distribution well. Then if we can find it, we estimate parameters of this distribution, and then we use these parameters to describe and compare the data. Then how we use the parameters? Well, any theoretical distribution has several functions. First of all, it's a PDF. It's denoted by a small f. And PDF, it describes a shape of your distribution. So in fact, it describes the density of probabilities. So by looking at PDF, you can see how your values behave. Where are the most expected values? Is it symmetrical distribution or not? How big the spread of the values is, and so on. The second function, it's a CDF, which is denoted by a capital F. So it's a cumulative distribution function. So it's a function that always gives you a probability to find a value equal or below given. For example, if you have, let's say, value 56, you can call CDF for this value, for this particular theoretical distribution with a certain parameters, and then CDF will return you a value between 0 and 1, which will be a probability to find a value equal or below given for this particular distribution. Then sometimes you need to do the opposite, meaning you know the probability and you need to find a value, like we do it with quantiles. In this case, you need to use inverse CDF function, or ICDF, which is denoted by f minus in minus 1. Okay. Now let me give you one more example of using CDF and ICDF. So we have, for example, the following case. You have a theoretical distribution that describes quite well the distribution of height of people in a particular country, for example. So you would like to know how many values, or what's the probability to find a value between 160 and 170 centimeters. Okay. So in this case, you know the values. So the values, you know the values. Values are known, but the probability is not known. Okay. So that's the case for CDF. So I will make two drawings, one with so this is a PDF, for example, that's the PDF of our distribution. Okay. And then, for example, this is a CDF for our distribution. Okay. So this is the fx, and then this is the small fx. Okay. And this is x, this is x. So let's start with a PDF. Let's say you have 160 is here, and 170 is here. So the probability to find a value between 160 and 170, or in other term, if you measure a height of one random person, what's the probability that this height will be between 160 and 170? We know that this is the area under the PDF curve. Okay, so that's the integral for the fx between 160 and 170. But if you use a CDF, you don't need to calculate integral, because CDF exactly gives you this value. So this is 160, this is 170. Okay, so you need to find, first of all, you need to find the probability for 160. It's this one, so it's f of 160. Okay, then you need to find the probability for 170. It's this one. 170. What means probability? It means that the probability that your value will be 160 or smaller, and then this is the probability that your value will be 170 and smaller. So the difference between the probabilities, f of 170 minus f of 160 will be the answer to this particular task. Now let's talk about ICDF. So for example, you want to find what is a 90% of most common or most expected values. Most common or most expected values. We will do quite a lot of these tasks, finding different intervals of most expected values in this course. So again, I will start with a PDF. So this is our PDF. This is the curve. Doesn't matter how it looks like. So this is x. Now think, what is 90% of most common values? It means that it's something not extreme. Okay, so if we have 90% of most common values, then it means that we assume that 10% will be the extreme values. Okay, extreme. And we may have extremely high or extremely small values. So let's take 5% here. So this is 0.05 or 5%. Okay, And the same here. So this is 0.05 or 5%. Okay, 5%. So this is A and this is B. So how many values we will have inside A and B? That's exactly 90%. So 90% of most expected values, because usually extreme values are rare. So we do not expect to have extreme values usually, right? In this case, it's very difficult to identify because we can't just take an integral, because we know the area already. We don't know A and B. What can we do is to use the ICDF. So think about what the A value is. What is A value is? A value, it's a value that has a border between 5% of the smallest and 95% of the largest. So it means that 5% of the values, all values in your distribution, are below A. Okay? How to find it? We know that that's exactly the task for the ICDF. So we can just call ICDF like this, and it will give us A. Okay? What about B? Well, B means you have, it's a border between 95% of the smallest values and 5% of the largest. So it means that we have 5% of the values, all values in our distribution are larger than B, and 95% of the values are smaller than B. Okay, 95% of the values are smaller than B. So we can just call the ICDF. You remember ICDF gives, CDF and ICDF always gives this probability to find the values smaller or equal. So in this case, we call the ICDF for 0.95, and it will give us B. Okay. So if you want to find the values for given probabilities, it's a task for the ICDF. If you want to find the values for given, if you want to find probabilities for the given values, it's a CDF.